Good morning, my name is Henrique, and this work was also developed by my advisor, Dr. Helen Durand. I will present this work entitled Data-Driven Modeling in Control with his thoughts on formulating a general optimization-based materials design problem. As a motivation to why we'd like to develop a general optimization-based materials design problem, we may consider the large applications of materials from a chemical and physical perspective. They are key to advance our engineering capabilities to meet requirements, such as the ability to withstand loads or being able to respond to the environment in a desired manner. However, it can be very challenging to design the right material that will enable a given engineering application to be possible. To date, there are no general and computational methods available for developing materials that can achieve given goals. Examples of current computational approaches include artificial intelligence techniques based on prior data and optimization-based approach using structured property relationships. They assume that certain classes of types of material are considered. However, a major challenge to formulate and solve a general optimization-based material design problem is the development of computationally tractable techniques for finding optimal materials that cross classes and types of material. A key issue of formulating this general optimization method is the requirement to select decision variables, objective function, and prediction of material properties from selected information about the material. Specifically, the model selection could impact the decision variables. For example, by using molecular dynamic simulation, equilibrium, dynamical, and structural properties can be predicted, but they may not be inaccurate if the force field models or potential functions, for example, are wrong. Therefore, an optimization-based materials design problem must consider how these would be selected. A potential decision variable used in molecular dynamics-based model includes, for example, the number of molecules of each type. The objective function may be an average value of a property that can be obtained from the MD simulation. In terms of the main challenges, and we have the computation time and specifying a molecular level with specific quantities. For example, at every iteration of the optimization problem, there is a need to compute the relevant potential interactions between a newly unselected molecules. It's interesting that the challenges of both computation time and model uncertainty have been tackled in process system engineering using reduced order and data-driven models, for example. So in the remainder of this talk, we'll discuss some of our recent work focused on data-driven modeling considerations in advanced control. I'll provide some preliminaries for this presentation by starting with the class of systems we are looking at. So we consider that the state, input, and disturbance are all bounded. We'll also consider that the process is stabilizable, meaning there exists some control law, in which here we denote as h of x, that is able to drive the process state to the origin. And the way that we will evaluate this mathematically is via LYAPUNOV functions. A LYAPUNOV function can be thought of as being like the energy of the system because it takes the zero value at a steady state and takes larger values as you move away from this equilibrium point. So this general terminology can be described by this figure here. We have this open set D, where the time derivative of the LYAPUNOV function is negative, and we also have this region omega rho. This is called the stability region, which is a set of initial conditions where if you start the process state within the region, under the controller h of x, the process state remains in omega rho, and in fact, it will be driven to the origin, which is reflected by this blue trajectory here. We also assume a class of empirical models, which is only a function of the states and inputs. In addition, we assume that this empirical system is instabilizable in the sense that exists an explicit stabilized controller, H and L, that renders the origin of this empirical system asymptotically stable. Also, there exists a LYAPUNOV function on V hat, which satisfies this inequality constraint. We now define a general formulation of a state feedback economic model predictive control. The main characteristics of a state feedback EMPC are the criterion for optimization. So we have a general objective function that does not require to take any specific form, an internal model that allows the prediction of future behavior. This could be a first principles model, and in this case, because the nominal first principles model is known and has a physical basis, and the economics-based objective function and the state constraints can be accurately evaluated. However, if empirical model is used instead, it's unclear how the economics-based objective function and the state constraints are adequately determined based on this empirical system. So techniques are needed for obtaining functions f and l automatically and online with a physical basis, which may increase the accuracy of the empirical model for better state predictions. However, that general state feedback in EMPC formulation does not address issues such as whether or not exist control actions that cause all the constraints to be met, and does not guarantee that you have closed-loop stability. So as a result, there are many variations on the EMPC formulation to try to answer these questions. And the one that we'll be using in this work is the LYAPUNOV-BASED EMPC or LYMPC. These are two-mode control design, where the first mode is associated with allowing the process state to vary over time within the design stability region. And the outcome of this is that we are able to guarantee that the closed-loop state is always maintained within the stability region omega rho by using this control design, even in the presence of disturbances due to the properties of the LYAPUNOV-based controller and the constraint design. The second mode of operation is that shown here, where we have this blue contractive constraint, and what this constraint does is that it forces the process state to a neighborhood of the origin or steady state. For the LYMPC design, motivated by the fact that an appropriate objective function and constraints may need to be derived from process physics and chemistry, prior works have suggested the use of empirical models for an initial EMPC design if a first principles model is not available. Particularly, the goal is to collect additional data using this initial EMPC for improving the understanding of the process. The controller could be used, for example, to gather data with a certain structure that may unveil a physical form, or non-training data that can verify model assumptions. And after this information is collected, the model used by the EMPC can be updated to a more physically meaningful model. That initial EMPC formulation can include, for example, on and off terms delta in the objective function and constraints to gather non-routine operating data for improving the process model. In this case, the controller could drive the closed-loop state to a desired information xd. However, to determine what desired data is may be challenging. As an attempt to answer this question, we may consider online control-assisted model structure selection approach, which choose accurate models among a set of potential model candidates. Well, this suggests that desired data should be that which quickly discriminates between the model candidates. So for this purpose, we may take advantage of the LYAPUNOV-based methods, which include guaranteed closed stability, incorporation of process constraints, and a free-form objective function that could facilitate model proving maneuvers. This would allow the most suitable model structure to be selected. To distinguish between good and bad model candidates, we define a threshold, an epsilon m, that represents how accurately the model candidate can approximate the predicted state to the desired data. So this approach, called Smart Data Gathering EMPC, has the following formulation. Specifically, we assume that there are MEC models which have nested stability regions, and the EMPC formulation maintains the closed-loop state in the smallest stability region of operation. Also, we assume that a sufficiently accurate model is included in that set of MEC models. The implementation strategy of the Smart Data Gathering EMPC is to automatically select non-routine data points by computing control actions that would maximize the information content, that is, data that would discern good models from poor model candidates. This can be achieved by maximizing the distance among the state trajectories using the ith and jth models. In addition, if the difference between the predicted state using the ith model and the measured state at decay is above the threshold epsilon m, the ith model candidate is discarded from the set MC. This could potentially reduce conservatism in the LMPC formulation the next time we would apply the data gathering mode. This is because we may remove models with the smallest stability region within the set MC. Now we provide a chemical process example that consists of a continuous stir tank reactor given by the system of equations. Particularly, the control objective is to operate the system in a data gathering mode while maintaining the closed state in the stability region. So we'd like to maximize the distance between the state predictions and based on all the models available in the set MC, which is reflected by this objective function. The manipulated inputs are the inlet concentrations T0 and the heat rate Q, and the process model is in the input affine form. The set MC contains these two model candidates available with different rate law parameters, and both process models share the same origin at the steady state. For the LMPC formulation, we designed the LYAPUNOV-based controller HI of X for each model candidate using Sontag's formula. The LYAPUNOV function has this quadratic form, and the parameters of the stability regions are provided here, with the design stability region using model 1 inside the stability region using model 2. The process was initialized at steady state and simulated over one sampling period. And the EMPC is applied only in a data gathering mode. Its prediction horizon it was set to be 1 to help with feasibility. And the prediction error metric is given by this expression where x1 at tk corresponds to the state measurement at tk, and x bar and ji corresponds to the prediction of the state I at tk using the jth model. With this scenario and without any disturbances, the threshold for this error metric was set to be 0 for the accurate candidate model and 12.24 for the inaccurate candidate. With bounded disturbances, the threshold was set to be close to 0.03 for the accurate candidate and 12.27 for the inaccurate model candidate. Using that error metric, we were able to discern between good and bad potential model structures. And as you can see here, both state predictions were maintained within their respective stability regions. The red line represents the state predictions using the correct model, and the green line corresponds to the state trajectories using the incorrect model, which has the smallest stability region. In conclusion, the optimization-based material design problem is a challenging task, particularly the materials modeling techniques can be data-driven and computationally intensive to work. In addition, the robustness of the solutions to this optimization-based problem is crucial since we desire that the optimal material identified from this algorithm have the predicted properties. To obtain insights into this problem, processes and engineering strategies can be investigated. Specifically, we look at data-driven modeling in optimization and based and control designs. And in light of this, we developed a smart data-driven EMPC that automatically determines which data to gather online to remove inaccurate model candidates from a stabilizing controller formulation. This allows the selection of the most suitable model structure available within a given set. However, the investigation of techniques for data-driven modeling with robustness for optimization-based materials design remains an open research direction. With that, we'd like to thank the Air Force Office of Scientific Research, National Science Foundation, and Wayne State University for their financial support. Thank you very much for your attention.